Okay, so now we take the Z in, Z out AV that we calculated, and we draw this into the final AC voltage model. At the end of the day, we don't really like current sources. The AC equivalent circuit uses a current source. We have a hard time wrapping our heads around current sources, so we need to draw those as voltage sources. So here's your generator, which has a 50 ohm output impedance. That gets connected to stage 1, which is going to have a Z in of 16.5K. It has a voltage amplifier, which is minus 0.6 times V in, and a Z out of 1.5K. That goes to the next stage, which is also the same values. 16.5 minus 6.1 times V in, Z out 1.5K, and the load resistor, I think at the end of the day it was also 1.5K. So now that we've got this built, we can then figure out what the overall voltage gain is. If I apply an input voltage, this is V in here. This is the supply voltage, which you don't actually have access to. It's in the back of the generator. You only have access to the point after the 50 ohms. So I would call this V in and this V out. So if I applied 1 volt into this circuit, so if I apply 1 volt into this, 1 volt would appear here. This would be minus 6.1 times bigger than 1 volt. But then I would hit this voltage divider. This voltage across here would hit a voltage divider. So that would be 16.5K over 1.5K plus 16.5K. And then it would get amplified again by 6.1. And then it would get attenuated again by a 1.5K in series with another 1.5K. Multiply all those numbers out, and I think you come out with gain of about 1718. I'm going to let you, so AV loaded with this attached is approximately 17 end-to-end voltage gain. And when we did the circuit, in the actual lab, we put a voltage in here of about 0.1 volts, and most of you guys got about 1.7 volts out.